Chapter 5. We are going to talk more about triangles.
I've already mentioned this before. You're gonna know more about triangles than you've ever cared to know before.
There's just so many amazing things about them. So last chapter, we just took a test over proving congruent triangles. Now our focus is on some properties of them. All right. And actually yesterday, or today, you're watching it in the evening, today you guys did a little construction of exploring perpendicular bisectors and angle bisectors.
Yes.
So this first section is just going to kind of elaborate on what you guys explored, what you hopefully noticed already. There's some theorems that go along with it. But nothing today is directly related to necessarily a triangle.
Right.
Okay? So today is just more, let's understand some perpendiculars and bisectors, and then we're going to take that a little bit further tomorrow.
Right.
Okay. All right, so let's recap real quick. We know a segment bisector.
Yeah, we've talked about that before. It's just, when I say it's bisecting a segment, it's dividing a segment into two congruent segments.
And a segment bisector could be a line, it could be a ray, it could be anything. So like,
could be a plane.
Yes. So let's say you have a line, and if it bisects segment AB, it's going to divide it into two congruent segments.
Exactly.
Right? This right here, this point is going to be your midpoint. So by definition, segment bisector really intersects that midpoint, which means that it's dividing it into congruent parts. All right, angle bisector. What is it?
That is what's dividing our angle into two congruent angles.
And a lot of times you see a
ray. Usually it's a ray.
Usually. Yep. And you guys explored an angle bisector earlier today.
Yes.
So dividing into two congruent angles. Now the other thing you explored was the perpendicular bisector. And this was somewhat a new word for us. Both Mrs. Oakribby and I've mentioned it, but we haven't used a lot with it. So think about the word perpendicular and bisector. All right, and we gave you this definition in class today so you could explore it a little bit. But it's a segment, ray, line, or plane that is perpendicular to a segment at its midpoint. So essentially, it's doing what to that segment?
It's going through its midpoint, so it's dividing it into two congruent segments, but it's also perpendicular to it as well. So we know an angle relationship, and we know some
it's going to form a right angle, and it's going to create some congruent segments.
Yes.
All right. So in this case, this line CP is the perpendicular bisector. All right. And a lot of times you'll see a line, you'll see a ray, even a segment. All right. So this is the perpendicular bisector of segment AB. What you explored today was something about a perpendicular bisector. So we're going to talk about that in just a minute. All right. Another term, lots of vocab in this section. Equidistant from 2 points. Now this word equidistant is something we need to get comfortable with.
And it kind of sounds like equal distance.
Yeah. So this idea of the same distance or equal distance, I like how you said that, Ms. Oakribby. It says a point that is the same distance or equal distance from one point as it is from the other. So like in this picture up here, I already know that the midpoint P, this is your midpoint, is technically equidistant to
A
and
to
B. So I could say P is equidistant from A and B because of the fact that we know it's the midpoint.
Right.
The one thing about equidistant is talking about the actual measure. So you're talking about AP is equal to PB.
Right. We're not talking about segments being congruent. The measures that are equal. Okay. So we've talked about the distance from a point to a line a little bit before. And just that when we've got a point to a line that there's, we've talked about trying to find a line that was either parallel or perpendicular to that line that goes through that point. Well, when we're talking about the distance from a point to a line, would you agree that there's lots of ways that I could do a distance to that line, right?
Yeah, but how do you know which one? Because they're all different.
They're all different. And the way that we're going to know which distance we want is we want the shortest distance, which is going to be the perpendicular distance. So when we talk about the distance from a point to a line, it's the length of a perpendicular segment from the point to the line.
So would this be also if I finding the length from a point to like a ray or a point to a segment,
Absolutely.
it's still going to be the perpendicular distance. So, again, the shortest distance. I like how you worded that.
Yes, because we know that there's lots of distances that I could measure. The shortest distance is always going to be that perpendicular distance. And that's going to be, it's the most direct route.
Okay.
And that's where we want to go when we're talking about finding the distance between that point and that line.
And you kind of saw this today when you were exploring something. This is something you're going to hear a lot. This is not only just today. You're going to see this in other chapters. So remember that perpendicular distance, like Ms. Hilbrich.
Anytime that you see that you're trying to find the distance between two things, like a point and a line, from a point to a segment, a point to a ray, it's always going to be that perpendicular distance.
That shortest distance. I'm going to write even that down too. Shortest distance that she mentioned there. All right. So speaking of that, if you're talking about something being equidistant from two lines, they're talking about a point being the same distance from one line as it is from another. But from the last slide, Ms. Hograve explained it great. If you're measuring the distance from a point to any line, a point to any segment, any ray, what kind of distance do I need?
We always want the perpendicular distance.
So I can't just draw any distance here. We want that shortest distance, so I'm going to kind of eyeball that. So let's say that's your perpendicular distance. And if I'm going to measure from here to here, I want, again, that perpendicular distance. Yeah,
that's pretty close.
That looks pretty good. Not exactly. We're just eyeballing it. When we do this, we want to actually measure it. So if I was talking about this point being equidistant to these two lines, I would have to first measure those distances to see if they are. And if they are, then those distances are the same length, same measure, right, which and then mean we can say they're congruent as well. All right? Mm-hmm. So just again, a reminder, when you're talking about measuring the distance from a point to any line, so any one-dimensional thing, basically.
Right.
We are going to be talking about the perpendicular distance.
Every time. Okay. Now, that's really leading us into our perpendicular bisector theorem. And this is one of those theorems that most of our theorems, we usually end up proving things to be congruent. And this is one of those theorems that's different because it doesn't do that. And let's read through what it says. It says, if a point is on the perpendicular bisector of a segment, then it is equal, so it being that point is equidistant, so equal distance, from the endpoints of the segment.
Okay, a lot going on in this. So first, when you were reading that, it says if a point that's on the perpendicular bisector of a segment. So
I'm looking at
C could be on it, and I also could say technically P is on that.
P is on it also.
Let's just talk about C first.
Sounds great.
All right, and you're saying that based on this theorem that point is equidistant, so equal distance from the endpoints, and the endpoints are A and B. So
right.
Ms. Hograve is drawing in those distances for you, which you won't always have drawn in. Okay?
Right.
But just to kind of get a better visual of what she's talking about. So that means, based on that theorem...
So if I know that C is on the perpendicular bisector.
Okay. So it's on that perpendicular bisector. And what's the perpendicular bisector? That's CP.
So we're talking about CP. Okay. Then what we know...
I'm going to be able to say that C is equidistant to A and B, which really essentially means AC and CB are equal, right?
Exactly. And I love that you said that they're equal. AC and, would you say CB?
Or BC,
yeah, I
however you want to do that.
BC are equal. And I love that you said that they're equal because equidistant means equal distance. It does not mean congruent. Okay. Most of the theorems that we've been using so far, we've talked about how when I've got this term, I know that it tells me that there's pieces that are congruent.
Like angle bisector means congruent angles.
Exactly.
Perpendicular bisector means congruent segments.
Exactly. So the perpendicular bisector theorem, and we're just going to write it as perpendicular bisector theorem, just tells us that it is equal distance. So it's telling us something about equality rather than congruence. So if I'm trying to prove triangles or anything congruent, which we'll see later, then I'm really going to have to turn that into a congruent statement using that definition of congruence. So just something to kind of keep your...
And something that I'm thinking about while you're on this slide is that on this particular theorem, this is something new. And a lot of times people, when they see perpendicular bisector, they want to only think of the definition. The definition helps, but it's not the only thing we need to know.
Right.
So knowing this theorem is going to help us in a lot of cases. It allow us to do things a little quicker sometimes. So just keep that in mind. That's the purpose of a theorem, is to allow us to do some shortcuts.
Now, I just want to kind of draw your attention to something that I think is pretty cool about this theorem, because if you look, what do you notice that we formed with these segments that are equidistant?
Well,
so
I see actually two triangles.
Yeah. And what do you notice about those two triangles?
They're actually congruent triangles.
How did you know that?
Well, you could. Here's the deal. What if I didn't know this theorem? You could prove those triangles are congruent without the theorem.
Because we could have said sides are, we know that a midpoint.
Yeah.
We've already talked about midpoints. And we could talk about this reflexive side. And we could talk about the angles being congruent.
So I could prove those triangles are congruent by side, angle, side, which then proves why those distances or those segments are congruent, which means then they're equal. So that is
that is the proof of that theorem.
Yeah.
So what you're really doing here is you're finding those missing pieces, those missing sides up to make those triangles. But we know that those triangles are congruent. And I think that's kind of a cool thing to see that. So this isn't anything all that far off. Now, here's what I want you guys to realize is that I could have any point on this line.
Yes.
I could have point, I'm just going to call this point, I don't know, where am I?
K.
K. Point K, I know that that point is also equidistant. So if I know that K is on the perpendicular bisector, so K is on, I'm just going to go ahead and call it CP.
Line CP.
Oh, didn't really mean to do that. On CP. Then what do I know?
That KA is equal to KB.
Do we even have those drawn in, those segments drawn in?
And you don't need to.
And we don't need them.
No.
But we just know that it is going to be equidistant.
And we know, obviously, point P is also on it, so we could say PA is equal to PB. But you could also have other reasons, since we know that's the midpoint, things like that.
We could say that they're congruent. Now, be careful, because if you say that they're congruent, you better be using the midpoint, definition of midpoint. But if you say that they're equal distance, then you could say that's because that's the perpendicular bisector theorem.
Okay, so the next theorem we're going to learn is essentially the converse of this. Okay. So if you think about it, converse is just flip-flopping it.
Right.
So you're going to be given basically some equidistances, right? Then you'd be able to prove what?
That it's on the perpendicular bisector.
You're exactly right. So it's the converse of the perpendicular bisector theorem. Essentially what we kind of mentioned, what that was going to happen, let's say you have a point that's equidistant from the endpoints of the segment. Okay, so kind of get an idea, if you were looking at the picture, what I'd have to give you. Then it's the point, is on the perpendicular bisector of that segment. Okay, so what this is essentially proving is that we're going to end up with a point that's on a perpendicular bisector, which then means we have a perpendicular bisector and we can say some things from that.
Sure.
So in this picture, what would I have to give you?
Okay, so we need a point that is equidistant from the endpoints of a segment. So I'm looking at like maybe point D.
Okay.
So if DA was equal to DB, so I've got that point that's equal distance.
And notice I don't even have it drawn in here. You could, but this point right here is the same distance to the endpoints of a segment, essentially.
Okay.
So that's what they're giving you. They're giving you these distances are the same.
Okay.
Then what can we conclude?
Then we know that it's on the perpendicular bisector of the segment. Well, I already see it's perpendicular to the segment, so I know that that DP has to be not only just perpendicular, but it's the perpendicular bisector.
So then I can say segment. then D is on the perpendicular bisector, which essentially is what?
DP.
Now that we know, and the cool thing about this particular theorem is now we know line DP is the perpendicular bisector, which then means, what else can we say?
Oh, that like AB is divided into two congruent segments, so AP would be congruent to PB.
So we could say that as well.
Okay.
So we could kind of, the converse actually allows you to kind of go further with some other things.
Okay.
You can then talk about perpendicular bisectors and things like that.
Awesome.
Okay. So
I've got a picture up here. And on this picture, it says, what segment lengths are equal? So let's just look for things that you notice in this picture that are equal.
Okay. So I notice right away CT and TD are equal.
Okay. And you know that because why?
They have the same length.
Same length. They're both marked with 7s, right?
Mm-hmm.
Okay. And looking at this, what else do you see as equal?
I see some congruent segments labeled CQ and QD, so that means they're also equal. Congruent means, in a sense, equal.
Okay, so this one we knew because their measures were marked, right?
Mm-hmm.
This one we knew, sorry, that is a QD, that looks a little ugly, because we knew that they were congruent, right? So kind of definition of congruence. And is there anything else you see?
Well, I don't see anything else labeled, so it's not obvious, but I do see a perpendicular bisector in this picture.
Okay.
And that's kind of the idea. So if I see line QP is a perpendicular bisector of segment CD.
Right, because you know it's perpendicular and it's bisecting that segment, then
we know that then any point on that perpendicular bisector is equidistant to its endpoint. So point P is obviously on it.
Right.
So then I could say the distance from P to C is the same as the distance from P to D. And that's because of your perpendicular bisector theorem. Now notice, I love what Ms. Hooker is doing. It didn't say explain, and if you had to do this on your own, you don't have to explain, but it's good to know the reasons, right? It's good. It essentially means that you understand it. You're not just guessing.
Right, exactly. Now, the second part of this says, explain why we know that T is technically on line PQ. PQ, we have our arrow to say that it's going to continue, but we aren't actually showing that where it crosses. How do we know that T will be on that line?
Okay, well, so can I just say, well, it's going to, because when I extend PQ out, it's going to end up being on that line?
Well, it is, but why? How do you know that? How do you know
so
that's
I can't really say because
I said so?
Because it looks like it's going to happen. No,
right. There's no because I said so theorem. Yeah. So
okay.
Can't use that.
So then what I'm thinking is what I know about line PQ is I know that it is perpendicular to line CD.
Right.
I know that about T. I see that T is the same distance to the segment that PQ is perpendicular to. T is the same distance from C as to D.
Right.
So if I know that a point is equidistant to the endpoints of a segment, then it's on a perpendicular bisector.
And I know that this is the perpendicular bisector.
So that means it has to be on it. So I would say the reason why is you could say because of the perpendicular bisector theorem converse.
Right.
Which essentially is what I was saying, is that because T is equidistant to the endpoints, then it's on the perpendicular bisector.
Exactly. So the whole idea that you can go either way. If you're given that they're equidistant, you know it's on that perpendicular bisector. If you know you have a perpendicular bisector, you know that they're equidistant.
Perfect. Let's do a proof. We can't do complete a day without a proof, of course. No, we'll have some days where we don't. All right. So we know based on the given that segment AC is a perpendicular bisector of segment BD.
Or segment BD, yeah.
So that's all they give you. Notice the given doesn't give you anything about anything specifically congruent. They don't do that. And the reason why I stress that is because we're trying to prove congruent triangles.
Okay, and I'm just looking at the triangles we're proving congruent. ABE and ADE. So okay.
These are the two triangles you're trying to prove.
Yes.
So I'm going to kind of outline that so you can kind of see.
Okay. Because like I was thinking, you know, my initial thought, we have a vocabulary word. So I was thinking to define it. And to define it, we could say that BC was congruent to CD and that we know that BC is perpendicular to AC, but that doesn't really seem to be helping me on this one really much at all.
And why is that?
Because it's not part of any of those triangles.
Okay, which you essentially could, but to me that would take a long way. And
yeah.
The reason why is because of the fact that you have those are proving stuff about these triangles or the two larger triangles.
Right.
So let's kind of
and not that we couldn't, because we could maybe do all of that and prove those right triangles to be congruent, then use some CP/CTC stuff. But I'm trying to think about the theorems that we've learned.
And I like that you're doing that, because perpendicular bisector, not only should you be thinking definition, okay? So when you see this, don't just think definition. Think about
The theorems also. Okay.
Okay.
Now, if I just saw a bisector, that's a different story. But when it's a perpendicular bisector, that's really special.
All right.
And that's where we've got these relationships. So, okay, I'm thinking about a perpendicular bisector is equidistant from the endpoints of the segment. Oh, I see a couple points on there.
Okay, so any point on the perpendicular bisector is equidistant to the endpoints of that segment.
Okay, so like A is on the perpendicular bisector. So I know that AB is equal to BD.
So I can just go ahead and say AB is equal to BD.
Now, I don't want to say segments are.
Yeah, you're right.
We are so used to writing segments are congruent.
Thank you
and
for
that's one
correcting
thing
me.
that we need to be really careful with on these theorems is that it's saying that they're equidistant.
Okay.
But I could also say that EB is equal to ED.
And what's the reason for all of this?
That's the perpendicular bisector theorem that says that any point on the perpendicular bisector will be equidistant to the endpoints of that segment.
And the nice thing about that is the segments she's naming, notice they involve the sides of the two triangles you're proving congruent.
Right.
But
they're not congruent statements.
exactly.
So, okay, let's mark our picture. We know that AB and AD are the same measure, which we're going to put the little tick marks, but don't be confused because we haven't said congruent yet. And we know that EB and ED are also the same. Okay, let's go ahead and make those congruent statements because we know that we're going to need those for the triangles.
While you're labeling it, you might as well just go ahead and state they're congruent. And the reason why we need that is because of the fact of we're proving congruent triangles, which means we need to state congruent stuff, not equal.
Right.
All right, but now we've got two congruent pieces.
Okay. Oh, and then I know that AE is congruent to itself. That's the reflexive property.
And this probably could be thrown in anywhere.
Yeah.
You could do that in step 2.
Okay, well now I've got my 3 congruent statements, so using side, 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 I can prove that those triangles are congruent.
So a little bit from chapter 4 still. That's not going to go away necessarily. You won't see as much proof in chapter 5, but the proof that you're going to see a lot involve congruent triangles, which is a good thing because you guys have shown that you know what you're doing with that.
Mm-hmm. All right. Now, we talked about the perpendicular bisector theorem. This next one is the angle bisector theorem. And there are some special relationships also that happen with angle bisectors. And it still has this word equidistant. So we're still going to be talking about equal distances, not congruent. I want you guys to realize that the definitions of these two terms, angle bisector and perpendicular bisector, their definitions talk about pieces being congruent because it's bisecting or forming two congruent parts. But these theorems talk about pieces being equal. So be careful with the difference between these. All right, this one says if you have a point that is on the bisector of an angle. So we've got a point here, D, that is on this bisector of an angle. And it's not really marked that it is, but
Let's label
we're
that.
going to say
Good
that we
idea.
are told that AD is that angle bisector. Then it, being again that point, is equidistant, so the same distance or equal distance from the two sides of the angle. Now, the sides of the angle.
Okay, sides of an angle are like usually rays.
They're usually the rays, yes.
Okay, so one thing that I remember earlier, and you even kind of explored this, is that when we're talking about a distance from a point to any kind of one-dimensional line, ray, segment, it's got to be perpendicular distances.
Right. And what you've got to be really careful with, because we'll watch kids do this a lot, is that it's when we say that it's that point that's perpendicular to, or that point's distance to the side, the point is D. Don't use AD as your segment that you're needing to do a perpendicular distance to. This is just a point D. So I want to do the perpendicular distance to that side. So I want to show that it's perpendicular to the side of the angle.
Not to the actual bisector.
Not to the bisector, because that's just the point that's on there.
Okay.
Okay. So I could even have a random point in the middle, and as long as I knew that that point was on the angle bisector, I'm going to be doing the distance, the perpendicular distance to those sides. and I know that that perpendicular distances will be the same.
Okay.
Okay? So again, think equal distances to the sides, not to the bisector.
Okay. Now, there is a converse to this one as well. So again, just flip-flop it. So this time around, if you are given a point that is in the interior, so it has to be inside the angle, and given it's equidistant from the sides of the angle. So one thing, again, when you see this equidistant, especially when you're talking about from point to a one-dimensional piece, you're going to be thinking of the perpendicular distance. So just remember that. So in this case, I would have to give you perpendicular distances first. So if I was essentially knowing what I was trying to kind of go at, this distance from D to B has to be perpendicular distance. That's what they're talking about.
Right.
They're saying then this is the point, lies on the bisector of the angle. So it's kind of similar to the perpendicular bisector theorem converse, all right, in a sense because of what you're trying to prove here. So if I give you, in this case, if I give you what? I have to give you
that like BD was equal to DC, then I know that DA is the perpendicular.
Yeah, so D is on the perpendicular, or not perpendicular, angle bisector. We're getting that mixed up, which is that ray DA, or AD, I mean.
Right.
Okay? Which essentially, I like what you said, that means ray AD is an angle bisector, which what does that mean? Well, that means these angles here are going to be congruent, which you can then go further with some stuff here.
Absolutely.
All right? Again, I think the trickiest thing about angle bisector or perpendicular bisectors is we want to think of the definition always.
Right.
Right? So
and let's go back to that last slide for a minute where we had that, because really, if I already knew it was an angle bisector, I had angles that were congruent there. I have a reflexive side. And I feel like, there should be enough right there to be able to talk about those triangles being congruent because we have angle, side to prove. So really seeing those right triangles, that's important, shows us that, again, those segments have to be congruent. So just kind of, that's another, you could have proved two triangles congruent first, but that's just more work we're not going to do.
Remember, the point of a theorem is allowing us to do it a little bit quicker.
Right.
Just like this one, you could prove this kind of case if I give you these distances are the same. This one's a little bit different. And I know that these right angles, they have a reflexive.
I could do HL.
Proved by HL, which then means
the angles are
CPC, these would be congruent.
These are just shortcuts, and they're really good relationships we need to know too. Okay. So we've got some examples up here, and this says, what can I say about angle CBA? It's just like you guys were at school, isn't it? Okay.
I know.
What can we say about angle CBA and angle DBA? And they ask us to explain too. So just looking at this picture, what do you notice that we have right now?
I do see some right triangles in a sense.
I do.
You do. Yeah. But I also am noticing you're saying something about proving something about the angles.
Right.
So I'm kind of trying to think about what we just talked about because I want to make sure I'm using new stuff, right? If we don't ever use it, then we're never going to get good at it. So I'm noticing that the distance from C to that segment CB and the distance from the A to that distance DB, those distances are equidistant because they're talking about that perpendicular distance.
Yeah, so we notice that because it's marked perpendicular, it's a perpendicular distance, and they're the same. So I can say that CA is the same measure as, AD. Okay, so I already know that.
Which then means that point A is actually on the angle bisector.
And what angle are you talking about bisecting?
Angle CBD, because, again, it's equidistant to the sides of that angle, which means that it's got to be on the angle bisector. So A is on the angle bisector, which basically means that those two angles, CBA and DBA, are going to be congruent.
Okay, so I can say that angle CBA is congruent to angle DBA. And what would be my reason there?
My reason would be the angle bisector theorem converse.
All right, because again, here we already knew that the relationship between that point and their perpendicular distances. Now I can say.
Now, you could go about this the long way, and like how I said, I see two triangles. You could prove the triangles are congruent, but this theorem allows you to do it basically in one step.
Right.
Where proving congruent triangles are multiple steps.
Right.
Okay. All right. What about this one? What does line CD represent?
Oh, well, I can tell just by looking at that it's perpendicular to a segment and it's definitely bisecting the segment. So it represents the perpendicular bisector.
Okay. I like how you worded that. Let's move on. It says, what kind of triangle is triangle ABC? Now, I see multiple triangles. Let's make sure we know what triangle we're looking at.
Okay, so ABC. So the whole big thing. Well, I know that... Oh, well, okay, I'm thinking back to the perpendicular bisector theorem. I know that CA and CB are the same, so it's isosceles.
Ah, and why are CA and CB going to be the same?
Because C is on the perpendicular bisector, so I know it's equidistant to the side.
So knowing this is a perpendicular bisector and that it's on it, that means these distances are going to be the same. So that means it's isosceles.
All right. And I am thinking back just to kind of refresh some of our memories of the stuff we've already talked about with isosceles triangles too. I also know that angle A and angle B are congruent because of the base angle theorem.
Good.
So just not that we need that.
You don't need to know that, but that kind of helps you.
Just something
now,
you guys
could
can
you
think about.
classify this triangle by the angles? You were kind of mentioning that. Do I know for sure if it's acute or right or obtuse?
Yeah, I don't know for sure.
No. We only know it's isosceles because of this idea that these are going to be equal because of this theorem.
Right. Last example. Okay. This one says find the following. And we've got several segments and an angle that we're trying to find based. It is just like you guys are at school.
You're here.
All right. So SW, class is not dismissed yet. Okay. SW, if you take a look at that, we're trying to find this measure. Is there anything we know about segment SW right now?
Well, I see SW is made up of two congruent pieces, and one of them is labeled 4. That means the other, so SU is 4, which means SW is 8.
Great.
Well, that was easy.
That was easy enough. Okay. The measure of angle VWX. Ooh, let's look at this one. VWX. So this angle right here.
Okay.
Okay.
Well, I see that it's labeled congruent to another angle, which is angle VWU. And I noticed that that angle is involved. The angle I'm trying to find it's involved in a triangle that doesn't really have a whole lot of information besides that that's going to be a right angle as well. So I'm looking at the other triangle UWV. That one, triangle UWV, has a right angle. It has a 50-degree angle. And the angle that's missing is the one that's congruent to the angle I'm trying to find.
Right.
Okay. And I know because it's a right triangle, so triangle UVW is a right triangle, its acute angles are complementary. So that 50 and that unknown angle add up to 90. So that means that unknown angle is going to be 40.
Great. And if this is 40,
that means that one's 40, which is the one piece that we need.
And again, if you don't remember the complementary piece, you could do triangle sum theorem also and say all of them together equal 180, but if I know this much of it is 90, then yeah, those two together are just going to be the 90. Okay, now let's talk about VU. VU. So this segment.
Okay, I'm noticing that it's a perpendicular segment. And because it's something we've been talking about, when I talk about perpendicular segments, a lot of times it's either maybe perpendicular bisector, which technically it is.
It is.
But I also, that's not really going to help us. I look at another picture on the other side. VX is also a perpendicular segment. And the reason why I'm pointing this out is because I know point V is actually technically on an angle bisector.
Right.
So a lot of these are connected somehow. So since V is on the angle bisector, which is that WV, then it's equidistant to the sides of that angle it's bisecting, which means VU and VX are exactly the same.
And they already gave us
VX, so that means VU is also the 3.36.
So I love how you looked and you saw that it was a perpendicular bisector, but it was also an angle bisector. It's really, there's a lot of relationships in this triangle, or in this one SWT triangle, but we really need to look at kind of what all things do we know, not just one piece. Okay, the last one says that we are going to find WX.
Okay, so a couple things that I'm seeing, because a lot of these things, there's a relationship to something else. I've noticed that. It's not, like in the beginning, it was pretty easy to find. I'm noticing that triangle UWV and triangle XWV are actually congruent triangles.
And why do you know that?
I could say by side angle side.
Yep.
Or no, I can't do side angle side because I don't know WX. That's what we're trying to find. Yeah. I could do by angle side. Angle side. Okay, so I know that, which
or even
means
angle side angle.
Which I can then say, or HL even.
Even HL, yeah.
Lots of reasons. So that means that their corresponding parts are going to be congruent. So
I'm going to redraw them real quick because I just got a mess of stuff going on up here. Sorry.
That's okay. Sometimes it gets kind of, I like that you're doing this.
WV.
Sometimes I confuse myself when I do it.
I know. And I see where you're going, but just so that way everybody else does too. WXV. So we know that this was our 3.36.
And those were both the same.
This was 3.36. These were both perpendiculars. This was 40 degrees, which isn't going to be helpful in finding a side. I'm going to leave that off for right now.
But I know that those are congruent.
I know they're congruent. I'm just going to mark that they're congruent.
I like that.
And we know that this was 4. Okay.
And so I know those triangles are congruent by angle side. So that means UW is going to be congruent to WX, which means since UW is 4, that means WX is also 4.
Right.
And that's what they needed.
Perfect.